of
RAM parameter. Nothing is a blackboard.
The whiteboard, yes.
The whiteboard, yes. So no, nothing is written.
Yeah, this is written, sir.
Apportionment
Allocation
or
of
allocation
RAM's
of RAM parameters. So what we are trying to do in this is, we have a system of a big system consisting of various subsystems. We have been given a reliability of 0.95 or whatever number for the whole thing. The apportionment really talks about how to allocate this 0.95 to these 3 components or 4 components or n components. So we saw one method yesterday, 2 methods. One is the equal apportionment, give everybody equal. So the reliability you divide by 1 by n, if n systems are there, will be the each system reliability. The second method we saw was the Aeronautical Research Institute method, ARINC method. There you decide a weighting factor, because depending on the complexity of the equipment which has got more number of components, it obviously is more likely to fail. So he must have lesser reliability, and the equipment which has got less number of components, we should have more reliability allocated to that, because this is achievable. So based on that, the weighting factor we saw, and we did that. And today what we are going to see is the next method, which I said, the agree method. Agree method is today's this thing. So what are the assumptions here? Here the assumptions are, we take, it is a series system. All systems are in series, which most of these things are naturally in series. And it containing n subsystems. N subsystems in series. Now, this is assumption 1. Assumption 2, each subsystem n suffix I equal to 1, 2, 3, n. Each subsystem ni has ni modules. No mistake here. Each subsystem I has ni modules. I is what? 1, 2, 3, 4, n. I equal to 1, 2, 3, 2, n subsystems are there. So each subsystem has got ni modules. Pictorially, how it look like? Pictorially, it look like this. For better appreciation, it goes like this. Each of these systems has modules. If I take I equal to 1, 2, so let us say this is ni. So each of them has got certain modules. So the subsystem n has got, this is a subsystem n, it's got ni modules, 1, 2, 3, 4, 5. Like this, number of modules are different in each subsystem. I'm going to drop it off. This subsystem has got ni modules, I equal to 1 to n. Then, since you are talking about reliability, the assumption 3 will be, I need an operating time. Reliability always associated with operating time. Now, assumption 4 is, it's a general assumption. Subsystem I, the operating time is Ti. Yesterday I told an example of a missile launching. Operating time of subsystem I. While launching, yes, some subsystems may need to work only for a few minutes. whereas the other subsystems have to work till the end of the flight. So this is general case. Each subsystem has got their own operating time for the entire system to work. Say for example, a starting button is there in a locomotive. It is a subsystem of that, but if it fails, you can't start the locomotive. But it doesn't work throughout the run of the locomotive. Only when you want to start, you press the button. So very short time it works. That subsystem works for a very short period of TI, whereas the engine works for a very longer time throughout the run. So the operating time of the system can be different from the operating time of the subsystem can be different from the operating time of the system in general. They all can be equal, no problem. But in general, TI can be the operating time of the ith subsystem. And next agree method, next assumption is it is assumed that not all failures would result in system failure. We'll give an example. Not that means though we have put in the picture all are in series. The first assumption says all the end systems are in series. You may ask, now we are assuming not all failures will result in a system failure. So these are contradicted. These two are contradict each other. If one of them fails here, system will fail. This is a subsystem Ni. We assumed in series, but here the assumption is that not all failures will result in system failure. Can you think of an example? A simple thing here would be maybe this subsystem has got an arrangement like this. So one fails, the other one is working, the chain is working. Chain will still continue to work. So this subsystem failure here does not result in the overall failure because this has got some kind of a redundancy. So this is one of the assumptions. Giving all these assumptions, now we have to, as usual for the previous method, the weight factor has to be the weight factor Wi for the subsystem has to be determined. Now, how do we do this? The next step is this. So let us take Wi weighting factor for the subsystem I be the probability that the system will fail the overall system will fail given that subsystem I has failed. Given that, so what do we mean by this? Probability that the system will fail. There is a probability that the entire system, what we had drawn, will fail, the whole thing will fail, given that the ith component of this, say let is this ith subsystem fail. If this fails, what is the probability of the total thing failing? As I said, that depends on what is the complexity of the system. If the system has got a very series parallel combination or something like this in the reliability block diagram, then there is a probability that this failure in this, the failure can be here or here or here or here, any one of the four, may or may not result in the total system failure. It depends on the structure of this. That is why you have to find the probability that the system will fail, from this end to this end, system will fail, given that the subsystem I has failed. This is a problem that you can establish, or you can, there are, for each, by experience, people have got different subsystems methods, or you can work out by RBD calculation. Okay. So we have defined what is WI. Now, what is the failure probability of the ith subsystem? Failure probability of ith from the general earlier knowledge, we know that failure probability of the ith subsystem is 1 minus e to the power of, it works for a time ti divided by mt tfi. General equation. This is r, 1 minus r. This is r. 1 minus r is the failure probability of the nth subsystem. Why we have started with this equation is, our aim is to find this. I know the overall MTTF. How do I get this individual MTTF? That is my purpose. So that is why I start with this equation. I put my variable. I'm interested in this parameter MTTF to find for the ith subsystem what is the MTTF. So I have put this. So this I just wrote because this parameter, the e power minus lambda t, lambda is 1 by MTTF is the reliability, 1 minus r is the failure probability of the ith subsystem failing, if you know, because Ti we said is the mission time for the ith subsystem, that is known. MTTF I do not know, which I want to find out. So I'm saying that failure probability of the ith subsystem is this. Now, the probability that the system survives, big system, the entire system survives and the ith subsystem fails. How do we do that? What is the probability that the system survives and the ith subsystem fails? So if this is a failure rate, the definition of WI is what? WI is probability that the system will fail given that the subsystem I has failed. Isn't it? Given that subsystem I has failed is this probability of. So this multiplied by WI into 1 minus e power minus Ti divided by MTTF I will be the probability that the system will fail given that ith has failed. Okay. Now, but the question here asked is probability the system will survive. So it will be equal to 1 minus. Is the probability that the entire system, the big system will survive if the ith subsystem fails. This is equal to 1 minus Wi, the weighting factor, which is the probability that the system will fail given that the I system has subsystem I has failed. Okay, think it over. It's easy, just multiplication of two probabilities. This is probability 1, this is probability 2. Multiplication of these two gives the overall failure probability, and 1 minus that gives the survival probability. Now, what agree method does is, once you get this concept, now we assumed a system something like this. And I also said the nth system has got the number of modules. Sorry, the ith system has got ni modules. 1 module, 2 module, 3, 4, to ni modules are available. The agree method, their suggestion is the reliability we know, this is given to me. Now, what is ultimately I'm trying to find out what is the reliability of this? What should I apportion? This I'm just first write, I'll see equation, then I'll explain. For this one component, this will be the overall thing which is known to me. Where n is total number of modules in the full system. Total number of modules in complete system. That will be equal to I equal to 1 equal to 1 to n I will be n. That means how many such things are how many modules are there? This. Each one has got more. I count all the modules. Total number of modules is the capital N here. Capital N. Total number of modules in the system. And Ni is what? Module in the total number of modules in the subsystem. In other words, I am apportioning it to the proportional to the number of modules in each subsystem. One has 10, one has 5, another has 100, another has 5. So depending on the, so if you, it's like equally, if you do equal, what you do? You will do r to the power of 1 by n. So I am not doing 1 by n because I am not giving equal. What I am doing is, okay, you have got n module, ni modules, so you will give ni by n. So if you multiply all these things, what happens? You get the equation. If I, for first one, second one, third one, the numerator here it will become n1, n2, n3, n4, n5 divided by n. So n1 plus n2 plus n3 plus n4 is equal to n. So it becomes 1. That is the given R. So proportional to the number of modules, you give the, you allocate the reliability. Proportion to the number of modules in each of the subsystems. So I must know the number of modules, which I know by design. Okay, this will have, we'll do one small simple example after this. So their approach is this. Instead of giving equal, I give the factor ni by n here, where ni is the total number of modules in the ith subsystem, and capital N is the modules in the entire system, counting all from 1 to n. So if one fellow has got only one module, he will simply have 1 by the total number of modules. If you have got 10 by total number of modules. So it is reasonable. It is something, an extension of equal apportionment, subject to the number of modules each one has got. Okay. Having done this equation, so now I have got the survival or the reliability of the system which is given to me. I am allocating to ith subsystem proportion to the modules they have got. So this is the reliability of the subsystem Ni. Okay. So I will equate this to previously calculated Wi into this is the survival probability. This equation, what are the things known to me?
Sir, your voice is breaking.
Oh, in this system, what are the things known to me? There is some signal problem.
So you can switch off your video. Maybe that's why the broadcast is slow.
So, video is on, is it?
Yes, sir.
One second. I'll just call again, 1 minute.
Okay, sir.
It's not just getting disconnected, man.
So we can hear you, sir.
1 minute. Now,
Yeah, it's clear.
clear now?
Yes, sir.
Okay. So, the board is all right?
What is all?
Okay. So, this is the survival probability of the subsystem by taking into the weighting factor. This is the failure probability here. 1 minus is survival. So, weighting factor multiplication. So, this is the reliability of the subsystem in terms of the weighting factor. So, now here, what all I know the overall system parameter. Here, I know how many total modules are there. I know the ith module, ith subsystem, how many modules are there. All I don't know is Ti is the operating time of the ith module, the mission time of the ith module I know. All I don't know is Wi. So if I know Wi, then I can get what is this factor. From this I can get MTTF. So you take logarithm on either side, all those things you do, you will get 1 by, you can verify this, 1 by MTTF of ith subsystem will be equal to minus 1 by Ti natural logarithm of, why natural logarithm? Because e power is there. 1 minus 1 R star Ni by N divided by Wi. I equal to 1 to N. So 1 by MTTF is a failure rate. So you inverse this, you will get that. So now here all the parameters are known except Wi. Wi is the only parameter I have to get. So this, how do I get Wi? Wi normally for complex systems is available. So once you know that, normally the process of finding out Wi is something like this. You give a questionnaire to the experts and tell them, okay, say a lot of metro experts, rolling stock fellows is there, give them a questionnaire. What do you think is the probability of if this subsystem fails, the whole thing will fail. So by experience, they scale it, they keep it. So they will tell you. Otherwise, you have to mathematically go to the RBD and do the analysis, which is more difficult. So, but as far as you are concerned, for your this work, WI I will give. If I have to give a problem on this, I will give the equation. I will also give the WI also. So you don't have to. You only remember the method, how we arrive, how the agree method has been arrived at. If you have any doubt, it's a little tricky. So once you get that, but in the problem, I will give you the equations. You don't have to remember anything. Now we will do an example. Which will give it out. Now I have got an armored vehicle. You know armored vehicle in the army? Armored vehicle has got. There are 5 subsystems. 5 subsystems. What are they? Engine, otherwise it won't move. Suspension unit, gearbox, wheels, and batteries. 1, 2, 3, 4, 5. There are 5 systems. Now the required reliability of this vehicle is 0.95 for a 500 hours of operation. On 500 hours of operation, 0.95 is the required reliability. So this is the statement of the problem. Now I will give you the data. So this is the subsystem, the waiting factor, TI, that is subsystem operating time, and the number of modules. Oh God. I think the board is gone, is it not? What is?
So can you send the link again?
Yeah, I'll do that one. I've sent it. You got it?
Yes, sir.
Okay. So we'll start afresh again.
Yes, sir.
So now I have to give the data. Problem we said armored vehicle, 5 subsystems, 500 hours reliability, 0.95. That is the problem statement. Now the subsystems. WI for each one, waiting factor. The subsystem operating time, that is TI. The number of modules in the subsystem. NI. So first is engine. It has a waiting factor of 1. If it fails, the whole system, definitely probability of failure of the armored vehicle is 100%. If the engine fails, the armored vehicle fails. That is meaning of the waiting factor. Remember the definition of waiting factor? What is the probability of the overall system failing if this subsystem fails? So if the engine fails, the probability of the total armored vehicle failing is 1. And we said what is the target time given this has to work for 500. Naturally, if the mission is 500 hours, the engine has to work for 500 hours. You cannot have mission 500 hours, the engine works for 100 hours. The number of modules in the engine is 120. The next item is gearbox. Gearbox fails, probability of the vehicle failing is 100%. The gearbox also has to work for 500 hours of mission time. It has got, let's say, 80 modules. Suspension unit. Suspension unit. Weighting factor is 0.9. Yeah, poor suspension, still the vehicle will move. So there is a 90% probability only. So 10% it can survive. With some, maybe vibration is more, but it will survive. And it need not work for all the 500 hours. I can manage with, say, 400 hours. It has got 40 parts. Wheels. The vehicle is waiting some places, moving some places. So it need not work all the time. Suppose I go to a destination after 500 hours and I wait there. So it doesn't matter. So there is a weighting factor they have assigned 0.8 for this. It's a matter of judgment. So it has got only 300 hours of operation because it goes to a place, work armored vehicle, works, it stands there, works for some time, then goes to another place, stands there. So when it stands there, the wheel has no job. So the wheel's mission time is less than the total mission time of 500. They have allotted 300. So it is 45 parts it has got. Battery. It is required only at the starting time, depending on the vehicle, is a petrol or this thing. Weighting factor is 0.9. So its operating time is only 100 out of that, and it has got 40 parts. So from this data, we have to work out. So what is the total number of parts? Total number of parts, N is equal to the sum of all these things, which is equal to 325. So I've got the capital N, I've got the NI, I've got the TI, I've got the WI. So I can work out the MTTFI from the above equation for each one of the things. So you can do this, check it up later. So you should get an answer of engine MTTFI is 26,400. Approximately you should get the gearbox 29,600. Suspension 57,004. Wheels 33,762. And battery 22,046. Something like this, you will get the answer. You can work it out. You can get the answer for this. Okay. Good. So I've done most of the things here. You have to only do the arithmetic. So in the exams also, you will get only problem like this, similar to this, where parameters will be given, tabulation will be given, and you have to only simply substitute and get the thing. Because that's what you are going to do in the office. You are not to derive the agree method equation in the office. You should only know how it has come. What is this weighting factor? How do they arrive at the weighting factor? It's only for that purpose I have given the derivation. The next method, the next step in the process is, so this is over. Agree method is over now. So I have gone from system to subsystems. So from N, which is NI, I have derived. Subsystem NI, what is the MTTF I have calculated. Now, similarly, the subsystem itself will have components. Subsystem is a small part, so it will have its own components. Total number of components may be M, V equal to I equal to 1 to N Mi. Total number of components I can calculate. Same Ti is operating time of each of these components. Lambda I or 1 by MTTI Fi is the thing, the weighting factor you have to get. So all those things are there. So it is same derivation, everything, except that it is here it is total number of subsystem, individual subsystem. Here it is total number of components for the whole work, and what is the component of each of these modules. So equation is the same, everything is the same. Okay. Now we will do a simple example in this. Now there is a module number I, number of components So the reliability will be M number of components of the subsystem into capital M divided by capital M, the total number of components. The first module has got, let us say, 20 components. Okay. The second component has got 40. Sorry, the third module has got 20 components. Fourth module has got 20 components. Total is 100 components. Given the system, reliability is 0.9. I am saying here all the components are equally important. If one of them fails, the whole thing fails. That is Wi equal to 1. Equal importance. Previous example we saw unequal importance. This is equal importance. So what will be this? Each one. You can calculate this. I hope there is no problem here. So the first one will be what? 0.9 is the overall, to the power of, it has got 20 components, divided by total number of components are 100. The second one will be 0.9 multiplied, has got 40 components, divided by 100. This will be 0.9 into 20 components, divided by 100. This is 0.9, 20 divided by 100. It's a basic simple assumption here because Wi is 1. So if you put Wi 1 there, it will get the same equation. So only it is distributed proportional to the number of components. Because it is exponential. Now if you add, for example, all of them, you can see 20 plus 40 plus 20, 20, 100. 100 by 100 is 1. So 0.9 to the power 1 is 0.9. That is the total thing. It's like 1 by n. All are equal components. You will do R of t dash to 1 by n. N systems. Each one is equally distributed. Since the components are different here, the apportionment is different. And the probability of one subsystem failing, making the whole system fail, is 1. That means they are equally important. So the essence here is between the ARNC method and this method is, there we took only the complexity. How many components are there? In this case, we are taking complexity, that is the number of components, also the importance. How important is the module? Whether it will make the whole system fail, then the probability Wi is 1. If it doesn't make the whole system fail, then it has a probability less than Wi. So I can afford to have a mean time between failure of small value. It means failure rate is more because it works only for a, it is not so important in the system. Its contribution to the success of the whole system is less. So it takes into account, the method takes into account two factors, that is the importance and the complexity in terms of number of components. The other method gives equal importance, only takes into account components. This is the only essential difference between the two. There are other methods, I am not going to dwell on that. These two is enough for you to apportion the system. As far as reliability apportionment is concerned, this module completes this. So you can see Ebling's book on the apportionment. There are some methods are derived there also. Not the yeah, some of them what I have taught is there in that. Okay. Hello, Vinay?
No, sir. That's my phone.
Vipin is available. There is one module I gave for the seminar, first seminar, which is compiled in a book form. Various sub modules of reliability.
Okay.
Hello.
Yes, sir.
In that book, there is one, 2-3 papers, 2-3 pages of write-up about this whole thing, agree method.
Okay.
Simple form. So people can refer to that book. Then that book it is there.
Okay.
Remember the first seminar we conducted.
Yeah.
We gave some important papers to them,
Okay.
repeating material.
Okay.
So whatever I have taught is there in that.
Okay. I'll collect it from Vipin.
You ask them to take them from the library and they can read it.
Okay. Okay.
Okay.
Yes, sir.
Now the time is over, or still there is some time?
So we've done 40 minutes, sir.
Oh, still there is some time. So I'll just briefly touch upon now. I have started with reliability as the given thing. Given for overall. Then apportion you get MTTF for the ith system or lambda I for the ith system. This is what we did. The overall is given. Then we apportioned this by two methods, got it to the subsystem level. The answer was an MTTF I or a lambda I. So the question is, supposing I am given only the overall availability, not the reliability. Availability. As the system availability, AS is given to you. So from AS system, I must get AN I for the ith system, ith subsystem. And once you get this, then if I know the MTTR and MTTF, from this, one of them should be known. Either MTTR should be known, which is most probably this is what will be known. So I go to MTTF because AI equal to MTBF of the ith system divided by MTBF of ith system plus MTTR. So from my experience of the past records, how much time it will take to repair? I have MTTR, so I know the individual subsystem availability. So individual MTBF I can calculate. This is another form of the problem. So the problem, the overall may be given as RS and the overall may be given as AS. And the main crux is to get to the subsystem availability or reliability. Once you get to the subsystem, that is a target. Then once you give the target, they will do the problem. So here also the methods are very similar, same thing like the previous one. To summarize, you give equal to all. This is the simplest. So if I given AS 1 by n systems are there, so it will be the AN. Simple problem. Then you give a weighting factor, ANI, WI weighting factor into AS to the power 1 by n, not equal, but something else. Now this weighting factor will also be given to you, depending on the experience, past this thing. People have worked out a lot of list database are available. This will be given. So once you first work out this equal, then you adjust. Okay, this is not so complex. So this has got a weighting factor of this much. So I give more availability to this or less availability to that and do that. Once you do one of the subsystems, is in fact is a little more simpler. Remember the problem we did in what did I do the problem? Yes, I gave maybe in the first class. I said the availability of various things in a metro, electrical, mechanical, that is rolling stock, SMT, civil. I gave a problem of that this rolling stock takes 50% of the availability, unavailability. Then electrical takes some 25%, SMT takes some 15%, civil takes some 10%, like that. I gave one problem and I asked you to find out what will be the overall is 99% availability. What will be the contribution to each one? I gave a problem, if you recall. This is the weighting factor. This is the weighting factor. How did they? Sorry, weight. This is the weight. Each one don't have equal. They have got different thing. How did they come to know this? From other systems. So it's a much simpler approach here, provided I'm looking at the availability of the total thing. So this weighting factor is available to you, so you can just do that. So the problems can be either you start from the reliability of the overall and come down to this, or you take the availability of the overall and come down to individual subsystems. Now comes the real issue. In metro systems, just think about it. Punctuality is given. Punctuality of 95%, 98% or whatever it is per corridor. Now this is neither reliability nor availability. The new word they have given, punctuality. What is the relation between whether I take it as reliability or I take it as availability, or what do I take this as?
So I think we lost the screen.
Screen is lost.
Yes, sir.
Minute. What do I do? Again invite.
Let me refresh, sir.
So what was the last one? Is it 25%, 50%, 15%?
Yes.
That you got?
Yes.
Afterwards, I have not written anything.
Okay, then no.
Okay, I'm only stating the problem because I'm concluding.
Okay.
I'm posing a problem to them. The problem is, now we have seen reliability of the overall system is given, how to go into the subsystem. Or availability of the overall system is given, how to go into the subsystem. Let us take a simple method of equal apportionment. Fine, I have apportioned, no issue. In the case of a metro, how do I specify these parameters? The management says I must get 95% punctuality. They neither use the word reliability nor use the word availability. They use the word punctuality. Now the question is, what do I understand by punctuality? What do you mean by punctuality? Do I take it as reliability or do I take it as availability? Because these two are not the same. Reliability is different from availability because availability has got a factor of MTTR into its picture. Whereas reliability depends only on MTBF. Availability depends on MTBF and MTTR. But the management or the client tells you, I want a punctuality of 95%. You do what you want. Now, how will I start? How do I convert this punctuality into a reliability figure or availability figure? What is meant by that? A lot of confusion goes on among the consultants, among the academic people, everybody. There's any number of papers, at least some 200, 300 papers are written. How do you define punctuality? Is it reliability or it is availability? This is the biggest issue of the whole RAMS thing. For as far as metro is concerned, in case of a plant, they give you the availability, the overall system. See, you've got a paper plant, a paper making machine. So they will tell you, okay, the overall availability will be, I must have an uptime of so much. That means availability. So you can go down further. Or sometimes they may say mission time. Okay, mission time reliability is given, you can go. So in metros and railway system, it is punctuality. There's a great debate goes on. So you can also think, you can also go through, search, find out how do I relate punctuality. Do I take it as availability? Then go down to the systems, one approach. Do I take it as reliability? Go down to the subsystems, another approach. So which one is right? Is the question to all of you. Please go through the papers. Then we will, this I want to discuss when I come back with you. Because there are a lot of discussion involved in this. One way monologue will not work. A lot of discussions will be there. So you have to participate. You have to say why it is so, why it is not so. So all those things you can ask. So, but meanwhile, please prepare. What is punctuality of the railway system? What is the relation between punctuality and availability, or punctuality and reliability? Do they have a relation? If there is a relation, what is the relation? Please take down your notes and keep it ready. When we come, we will discuss. Okay.
Punctuality and availability.
If you can solve this mystery with very basic things, a very basic understanding, then I think we have learned a lot about RAMS. All others are available in books. This is not available in books.
The relation
only
between
some practitioners only know it, how they do it. So from book you can find a lot of reference if you search in the thing. You have to put relation between punctuality and availability or reliability of train services. You put this heading, you'll find hundreds of definitions, this, that. So after that also you will not be able to conclude either whether it is reliability or it is availability. And what is it? It is a mystery. Still it is a mystery for many people. So you can see, then we'll discuss how to take it as which parameter and how to apportion. Apportioning, you have learned it. Once you know the top parameter, what is the definition of that, the others are easy. Okay. Okay, Benay?
Okay, sir.
Right.
Bye.